Thank you for the introduction. I think this is the last talk, so the purpose of this talk is to sort of entertain just give a little bit. So a lot of what I am about to say has been already introduced by Stefan aptly. And so I'm going to repeat a couple of points, and then I'm going to tell you a few, just a subset of actually two things that are interesting that we've been working on over the past, depending how you slice it, either over the past decade or over the past couple of years with some advances. So I'm going to make a couple of trivial points, but just to repeat what Stefan said. So this is basically a map, a visual map of optical spectroscopy, linear optical spectroscopy. You can, you change the wavelength of the light, and you measure a number of excitations. There's an enormous amount of information in a linear optical spectrum. Broadly speaking, in this region, which is the EV energy scale, you get charge excitations amongst different orbitals. In the mid-infrared, you have phonons and other things. And at longer wavelength, you have these collective modes that reflect either charge density waves or superconductors or excitomic insulators or what have you. There's also an enormous amount of information in the nonlinear optical response of materials even by a very sort of strict definition. I think there must have been 15 Nobel Prizes that have been based on shining light fields that are intense enough to on various materials to generate a number of nonlinear properties, nonlinear responses, including, but not exclusively, things like shining red light and getting blue light out, measuring symmetries, measuring transitions with different selection rules. But it's also true that 99.99999% of all the experiments that have been done in nonlinear optics have been in this regime. And the reason for this is that lasers are easy to come by at these frequencies. And it's very difficult to have high intensity light fields in the region that Stefan discussed right now. So there's now, because the technology has gotten good, and some of us have been wasting their careers trying to generate strong light fields at long wavelengths, there's an emerging field. So nowadays you can generate light that is tunable throughout the full spectrum that I showed you before in a setup that looks like so. So this is, a relatively complicated setup, but not a brain, not a brain surgery thing. I mean, it's just some, less than 1 million and a couple of students. And so this is basically the goal. You would like to have fields with field strengths that are of order megavolt per centimeter, let's say, or say higher than 100 kilovolt per centimeters. And you want to look at the collective responses of all these collective modes in their nonlinear regime. And so there's a number of things that you could, there's at least 2 things that you can do. So I will sort of, over the talk, I will comment more on what this megavolt per centimeter field means. But so you can slice this problem in 2 ways. So this is what Stefan talked about. There's a number of things that you can do, which are perturbative responses, meaning you drive an excitation. There is a linear response, which is larger than a second order, third order, fourth order, and each order is a factor of 10 smaller than the other. But you can, for example, drive phonons with a megavolt per centimeter field and an average polarizability of the lattice of a particular mode. You can easily drive displacements of many % of the unit cell directly with this mode. And this is something that Stefan talked about. You can also use, say, single cycle pulses where the current that is driven by one of these sort of short pulses becomes of order IC. So you start getting nonlinear responses of this type of short timescale. So this is one set of things that you can do. But there is also a very rich set of phenomena that have to do with non-perturbative responses. So one of the things, but not only, is this business of trying to amplify or de-amplify superconductivity. And this is something that we've been very interested in. And I will tell you at least one thing about it. So the idea is that you have a material that is either prepared or not prepared above TC, and you shine a light field at a certain frequency, and your goal is to control, meaning make pairing fields stronger or weaker, or in a material with a very high, say, mean field TC, but sloppy superconducting phase, you might want to couple to the phase coherence and synchronize or unsynchronize pre-existing paths. So this is, broadly speaking, the agenda. In the next 45 minutes or so, I'm going to talk about two things. I'm going to talk about, this is some map of superconducting TC as a function of year. And I'm going to talk about experiments in potassium doped C60, which are the ones, you know, a group, it's a subset of the experiments in which we've tried to amplify superconducting responses. And this, let's say, belongs to the non-perturbative regime. And then I will try to convince you that by studying the stripe phase of LBCO, we can make statements that, you know, that are new or that are or old statements in interesting ways, as these are, you know, by looking at the nonlinear response at terahertz frequencies of the single layer cuprate. So let me start with this business of exciting potassium 3C60 and other similar materials, or say unconventional superconductors, in the context of trying to amplify coherence. So the idea of enhanced superconductivity with radiation is actually a very old idea. Already in the 1960s, it was shown that if you take BCS superconductors and you sort of arrange them in microbridges and you irradiate them with microwave radiation at frequencies that are below the BCS gap, what you find is that TC goes up a little bit, say a few percent, and so does the critical current. So this is a non-equilibrium state. It's not a real phase of matter, but it has all the features of superconductivity. And there's at least one very famous explanation of these experiments, which was put forward by Eli Ashberg in the late 60s. And the argument is that basically what photoexcitation does is that it excites quasi-particles away, so it heats up quasi-particles, thereby reducing the density of quasi-particles at 2 delta and fooling the superconductor in thinking that it finds itself at a temperature that is lower than the temperature that is actually at. So it reduces the detrimental effect of quasi-particles at 2 delta, basically. And then there's a number of other experiments using UV radiation in these materials. These turned out to be more of an annealing effect. And unlike in this case, with these UV radiation experiments, people were never able to generate, you know, they could create a better superconductor, but they would never find temperatures that were higher than the highest possible temperature in one given class of compounds. But this is certainly something, you know, a very beautiful set of experiments that we should keep in mind. So over the past decade or so, and this, I won't talk about this, but Stefan has discussed some of this. We have shown, for example, that you can use light to try to remove stripe order in certain single layer cuprates. This was the first experiment done together with Hide, who's in the audience. And then there's a number of other experiments in these materials. These, by the way, have been confirmed by the San Diego group, who has basically shown that if you take LBCO and irradiate it in the same way, you can resurrect interlayer Josephson tunnel, interlayer superconducting coupling by removing stripe order. And in the YBCO materials, we showed that by moving the apical oxygen position to to and fro from the bilayers, one could induce transient features that were suggestive of superconducting tunneling at very high temperatures in YBCO. So there is a whole other set of experiments that have been done recently by us in alkali doped fullerenes, specifically potassium 3C60. There's some stuff in cesium that is not as convincing as the potassium doped C60, and also recently in some of these kappa BDT salts, in which by basically using a very similar protocol, we showed that if you're close enough to the antiferromagnetic insulator, say in this bromine doped kappa salt, we could induce signatures of transient superconductivity that are actually quite distinctive, all the way to say around 50 Kelvin for a 12 Kelvin superconductor. So up to where, anyways, we could. I'm not going to talk about this, but there's a whole set of observations that can be summarized. So most of my talk today will be about this class of experiments. So let me summarize how superconductivity in potassium dope, alkali dope fluorides works. So let's think about an FCC lattice where I put a buckyball at each one of the lattice sites of the FCC lattice. I put three alkali atoms, so I donate 3 electrons. So I have C63 minus at the lattice sites of this FCC lattice. This is a strongly correlated superconductor, which is, is well, and the physics is well summarized by this pressure dependent, either chemical pressure or external pressure dependent phase diagram, where for the largest alkali atoms, so the sort of the lowest hopping, one has a Mott insulator, cesium-3C60, which under pressure becomes a 40 Kelvin superconductor. And then potassium-3C60 is here, instead of going, it's still in the strongly correlated regime, but it's going toward more weak coupling type limit. Let's see. So the way we're going to diagnose, you can measure the conductivity, you can measure the Meissner effect. The way we're going to diagnose the emergence of superconducting order, or let's say of at least the conducting properties of a superconductor, is by looking at terahertz spectroscopy in this material. So the experiment is done like so. You have a terahertz probe, either time domain or using a synchrotron or a spectrophotometer. You bounce it off the crystal and you measure, let's say in this case, you can sample both the amplitude and phase of this, and you can measure both the reflection coefficient, but also the complex reflection coefficient from which you extract sigma 1 and sigma 2. And this is what you expect for a textbook case. You go from a situation in which you have a metal that has a plasma edge, but most importantly, a Drude peak in sigma 1 that has a finite conductivity here at 0 frequency, and then rolls down at the scattering rate. And again, a metal that has a peak at the scattering rate. As the material becomes superconducting in equilibrium by cooling it down, what one observes is that the reflection coefficient becomes 1 for all frequencies below the gap. This is for an S-wave superconductor, whereas in sigma 1 and sigma 2, I see all the spectral weight of the metallic charge carriers are being condensed in this pole centered at 0 frequency sigma 1, and then there's a gap that tells you about where the quasi-particles live. And then you can, although you're not measuring all the way to 0 frequency, you know that there is a pole at 0 frequency because sigma 2, which is the Kramers-Kronig, is connected by causality to sigma 1, diverges toward low frequencies. So the fact that sigma 2 diverges tells you that there's a peak at low frequencies, right? So if you took gallium arsenide, you would only see the peak, but you wouldn't get a divergent sigma 2. So, and this is now, if you measure in equilibrium potassium 3C60, these are powders that are being squashed in a pellet. You can measure this and you cool it down and you see this gap of about 4 some millieV. The reflection coefficient becomes exactly 1, especially if you extrapolate to 0 in the computer. But you very clearly see the sigma 2 diverging up to this number that tells you, out to here. And by fitting this, you can tell how big the superfluid density is. So these are the equilibrium optical properties of potassium 3C60 when you cool it below 20 Kelvin. It goes from red to blue. So a couple of ideas of how we think about the superconducting transition in this material. So this is the doped, 3 times doped C60 in its undistorted, non-existent life. It would be a high spin state because of Hund's rule. This is obviously a Jahn-Teller active type of situation. So what you have is that you basically, these materials acquire a low spin state. This is validated by NMR measurements amongst other things. And what you have is a 1/2 state in which you really have a superposition of all possible, these are supposed to be S1/2, sorry, of all possible configurations of all these electrons, three extra electrons in the molecule. And basically a combination of the Jahn-Teller distortion and also correlation effects give rise to A, the low spin state, and B, the coherent state, which gives you superconductivity. So basically, these fluctuations make it such that hopping between two buckyballs occurs at zero energy. Right. So this is work that was started in my group in, say, 2012 or so, 2013, by my student Matteo Mitrano, who actually had a, he sort of really did a fantastic job working on this. He's now joined the Harvard faculty, basically mostly on the back of these experiments. What he proposed was that, well, if it's true that you can, there's some fluctuations of the sort of the molecular cage that is connected to many infrared active modes that mediate the pairing and the coherence between multiple sites. In principle, one could use a mid-infrared pump pulse and make it resonant to the the vibration, the molecular mode. These are non-dispersive, high-frequency modes of these molecules, and sort of shake them in time, if you wish. There's a number of qualitative arguments, expectations that even at this level one could make. In principle, if you take the cage and you shake it, these orbital, you could have some stimulated dynamics of these orbital motions, basically, because as you distort the molecule in some direction, you will induce periodic modulations of the electronic structure inside the molecule. There is even a more qualitative argument. You can easily convince yourself that your Hubbard U is going to become periodic. Basically, the Hubbard U of the site is basically the capacitance of the ball. How much energy it costs me to put more charge on it. If you deform it in time, you could convince yourself that the charging energy of the molecule is going to change, and so you can think about the correlated electron problem now with the Hubbard U that is modulated in time. And then there's other arguments by which you could say that this shaking really, interacts harmonically with other modes and gives rise to average quasi-static distortions of the lattice. So, and many other things. So of course, this is all these non-perturbative dynamics of strongly interacting unconventional superconductors is not a very rational, but is maybe a few ideas that help us. So this is the first experiment that Matteo did. He pumped this mode. I mean, he had a whole rationale of how this mode would couple to the Young-Teller mode, but in reality, this experiment was done here because it was easier. So we pumped the highest frequency mode that we could pump, and then we had a probe pulse that was put here where you can see a large difference between the reflection coefficient of, this is sigma 1, I think. Let's say the reflection. So this is one of the, now this experiment has been repeated many times by many postdocs on many lasers. So it's probably about right. And what you find is that if you go to 100 Kelvin, which is 5 times above the thermodynamic TC, and you pump that specific vibration that I told you about, the light-induced state 1 picosecond after excitation, so 1 picosecond is going to become important at some point. What you find is that the light-induced state has the following features. The reflection coefficient is exactly 1, provided that you've done everything correctly in the way you reconstruct the optical properties. Your real part of the conductivity becomes gapped, and your imaginary part of the conductivity diverges pretty much to the same level that you saw when, to the zero temperature divergence of sigma 2. So it's as if you were taking all this red spectral weight and condensing it down with the right sum rules to maybe not a pole, but certainly a peak centered at zero frequency. Of course, this peak is going to be broadened by the lifetime, so it's not really a pole. But it's certainly, this is a very, let's see, the mobility of this, if you think about it like this, don't think about the conductivity at constant carrier density, the mobility is something like 15,000 of this light or higher of this state. So this is what was observed. And so for the purposes of what I'm about to tell you, it's useful to just think about one figure of merit for this that sort of encapsulates this. So we're going to use one model to capture both the properties of the metal and of the transient perfect conductor, or what gapped this state, this non-equilibrium state. So we apply the Drude model to fit both the red curves above TC in equilibrium and the blue curves below TC. There's no gap in this model, so one could do better than this, but you could take a non-gapped Drude model. And the advantage of this is that you can extract two things. You have a zero frequency conductivity and a scattering rate. And so this has the beauty that when the scattering time goes to infinity, so the scattering rate goes to zero, you can reproduce the low frequency properties, the below gap properties of the superconductor. And now sigma zero is a number that tells me about how many carriers or how many supercarriers I have. And so what I'm going to do is I'm going to define this extrapolated rho zero, which is the inverse of the limit for omega that goes to zero of sigma one. So I will know sigma zero with an error bar that is determined by how low in frequency I can measure. The lower in frequency I can measure, the better I can tell you what sigma one is. The sigma one in a superconductor would go to infinity, but even in an equilibrium superconductor, I could only tell you that this is some number 10 to the 14, between 10 to the 14 and infinity. And the opposite for it. So you determine sigma 1 in superconductor from sigma 2? No, I take sigma 1 and sigma 2, I fit them, I let sigma 0 and tau float, I keep the carrier density constant, as you'll see later, as a function of time. But basically, I'm taking this figure of merit that is the extrapolated zero frequency conductivity from my Drude model. Is this? Yeah, I mean, but you take the scattering rate to zero. I don't do anything. I just fit the data. And the data tells me, just let me say one thing. Because my data finishes here, I don't know if the scattering rate is zero. The scattering rate is lower than some number down here. This data here is compatible with a scattering rate that is either zero or some small number. Well, the blue data, I know what, no. This is a fit, sorry. Yeah. This is the data, this is the metal. I know the scattering rate from the metal because I'm measuring it down to a terahertz. And now I refit it as in the other state. And I know that the scattering rate is going to become lower than this number, but I don't know exactly how much lower. But I have the same problem. Yes. Yeah. Well, this is not the real part of the approach. With either, I take tau to. Right. Okay. This is. Yeah, but then I don't have the other. Absolutely. This is actually not the best plot. This was actually a plot I pulled out of something where we just put the lifetime of the state as the scattering rate. Anyways, but the error bars are calculated by taking let's see. This is the most optimistic fit you can get if you put the lifetime of the state as the scattering rate. Okay, and the lifetime is something I'm going to tell you about later. Yeah. If omega goes to zero, yes. For sigma 1, yes. In the blue data, yes. This is zero. But no. Equal zero is something else. That's yeah. Okay, let me say in a different way. A transient superconductor is a metal if you wait long enough. So the scattering rate is at time, the longest scattering time I can have is the lifetime of the state. To your question is, I have put a line here, where I have assumed in this specifically to this sample, where I have assumed that the scattering rate is the lifetime of the state. That's the highest possible conductivity that I. Okay, when you take this data here, there is a range of possible scattering rates that are compatible with this data. Okay. Yeah. The most in which, where is this? In which, let's say, sigma 2, you see it easier here, rolls over immediately here. The most optimistic situation is one in which the scattering rate, the scattering time, is the lifetime of the state, right? Which is measured in the experiments. And I apologize, but I put here the most optimistic situation, okay? In neither one of these cases is the scattering time infinity, because this is a transient state. Tell me yes, Andrea. Otherwise, we can't. No, I need you. This is the most important part. This is the most important part of the talk. So, yeah.
It would be beautiful to see in the real part.
Yeah, right. I mean, it's not that easy to measure below a few milliev. Yeah. Of course, you're fitting them both simultaneously. I mean, no, but this, let me repeat this. In this, you don't see the delta peak. This delta peak I made up, assuming that the scattering rate is as long as the scattering time is as long as it's possible, right? There is also far less. There are also far less flattering. No, you don't. What's going on here? Yeah. Well, I mean, if you, from the imaginary part, you could have a scattering. You could have sort of this thing that peaks out there, right? So, right. Okay. Apologies. I didn't want to confuse anybody here. Good. So there's an error bar that goes between this lifetime of the state and whatever the lowest frequency that I'm measuring. So now this was the early. See, now if you put this, take this rho 0, you plot it as a function of time. It goes from there's no error bars here, but if I showed you a log plot, you could see that this rho 0 goes down by anywhere between 3 orders of magnitude and many orders of magnitude. This is a linear scale. Okay. The problem that you have is that the lifetime is extremely short. The fact that the lifetime is extremely short gives you two problems. Problem number one, who cares? And problem number two is that the whole idea of this transient superconductor with a lifetime of 1 picosecond becomes very slippery. And this is testified by the conversation that we just had. So what we should do is to try to extend the lifetime of the state for various reasons. One, because it's better, and secondly, also because we can now try to apply new methods to study this. So what we did during the pandemic and before has been to try to develop a new laser, which allows us to drive these molecular nodes with pulses that are tunable between 100 femtoseconds and 1 nanosecond. So yeah, between 100 femtosecond and 1 nanosecond. So this is technically difficult, especially if you want to synchronize it to a femtosecond laser. So courtesy of German taxpayer, we've set up a whole sort of big laser which combines a CO2 laser with a large femtosecond laser, which seeds the CO2 laser and generates long pulses of 1 nanosecond, which are then sliced using semiconductor mirrors. So these pulses are sliced in the back and in the front using semiconductor plasma mirrors. And also a third part of these femtosecond lasers generates the same terahertz probe that I was using before, making it possible to do the same experiment that I did before, but by pumping with pulses that scale, that can be tuned between, say, 1 picosecond and a nanosecond. And what I would like to do is to do the same experiment with a constant number of photons. What I want to know is whether if I put 100 photons in 100 femtoseconds or 100 photons in a nanosecond, is the effect the same or not? And can I, by keeping the system simmered longer, can I create a longer lived state? Okay, so this is the PhD thesis of Matthias Budden, who did these unbelievable, and Thomas Gebert, who's a staff scientist in our department, and they've been really putting an enormous amount of work into this. these are sort of, this is sort of technical things, maybe for this audience are more than you are interested in. So this is now an experiment in which I am pumping with a square pulse, which is 1,000 times longer than the 300 femtoseconds pulses that I had before. And but basically with the same area as the one I was using before. There's a factor of 2 higher. And remember, before I was pumping here with 300 femtoseconds, and this thing was going beep, beep, and coming back in a picosecond. Now I'm pumping for 300 times longer. And now I'm probing here 100 picoseconds after the pump pulse is gone. The experiment is done at 10 hertz and not at 1 kilohertz. So the signal to noise is what it is, but it's still very, convincingly, I mean, we've done this many times. You see at 1 picosecond after the pulse is gone, you see that you still have this divergence or something that can be fitted with a divergence that goes in the same place where the previous one went. You have a gap and you have a reflection coefficient of order 1. This is larger than 1. Don't ask. I will talk about it, talk about this at the end of this. 1 nanosecond after the pulse is gone, I still have, so that's 10,000 times longer. No, this is 1,000 times longer than what I showed you before. I have indication of this metastable state, which has some rigidity in itself, with at least this really high conductivity and the gap state and the reflection coefficient of 1. The dots are the data. The lines are a fit. This is it, yeah. So now let's use the same figure of merit that I used before. I take rho 0, which is taken by extrapolating sigma 0 and doing the whole fit. It goes from the same number to something of order 0. Again, with some error bars. And it stays close to 0 for up to 12 nanoseconds. So 12 nanoseconds is the 1/e relaxation time. But after 1 nanosecond or so, this is more or less still 0. So now we don't have any more justification not to measure this with transport. This thing lives for 10 nanoseconds. So we ought to be able to see 0 resistance with transport. Now, there's a number of technical reasons why 4-probe measurements are very difficult at this speed. And basically, the reason for this is that anything that is capacitively coupled to something else, if the conductivity changes very fast, it's very difficult to keep anything that is capacitively coupled at constant voltage. But you can measure with 2 probes, work as hard as you can in trying to subtract the contact resistance. Hope that the contact resistance doesn't change with the radiation. Cross your fingers, and by being as careful as we're being as careful as we could, and we've seen that there is a resistance minus contact resistance as characterized before that goes to a level that is compatible with 0. Let's say. So this is the observation. So this is now right. So this is the last published results on this area. I'm going to give you, in this experiment, I'm going to give you a little bit of more advances. So this was the vibration. This is a tangential mode of the buckyball. But nowadays, we have learned how to build an optical device that allows us to move the pump anywhere we want, from here all the way down here. And so what my student, Ed Rowe, has done has been to measure this thing, I don't know, 50 times at every given pump fluence. COVID didn't have much to travel. So he measured this. And what he found, and specifically, he found this tangential mode at around 50 millieV, 10 terahertz. This other mode here, sorry. No, that's not what I wanted to show you. This other mode was at about, Stefan, what was this? Maybe 280 millieV or something, 300 millieV. 7 terahertz, sorry, 7 microns, 6.7 microns. And this one is now at 10 terahertz, 50 millieV. And what he finds are exactly the same results, and I'll show you the data later, but with 100 times more efficiency. So now instead, and I'll show you the efficiency. So this was the Matteo experiment, which at the time we thought, was something really very satisfying. And, however you fit this, the scatter has to do with the fact that the powders, every time you measure them, you make mistakes by a factor of 2 in the way you couple pump and probe into them. But pretty consistently, the efficiency, as measured in some way that I can detail if you're interested, becomes between 50 and 100 times more if you pump at 50 millieV. And when you pump here, there is no penetration depth mismatch between the pump and the probe, so the data comes out of the lock-in, and you don't really need to I mean, it's just very reliable data. You just, the reflection coefficient becomes 1. And so, you know, it's a lot more certain than before. Right, okay, so this is the efficiency. This is the efficiency which in this specific measurement is measured by taking the slope of how much spectral weight you're taking out of the metal as a function of fluence. This is a photosusceptibility somehow. Right, but I'll show you a resistance measurement now. Another way to say this is the extrapolated rho 0. Yeah, in the old measurements, you were taking rho 0, you were increasing the fluence, and it would go to this fluence would go to 0, some number which was of order 25 millijoule per square centimeter. By pumping at 45 millieV, where there's this resonance, if I pump at 0.2 millijoule per square centimeter, I already get on this specific data, I don't have, okay, for the previous experiment, I forgot to tell you, it was, you know, for the pulses, when we could stretch them, it depended only on the integrated number of photons and not on the peak intensity. That's the answer to your question. You know, it did. I mean, it depended on the area of the pulse. Right. 1 millijoule per square centimeter. As long as it was shorter than the lifetime of this one, we don't have any extensive measurement. What's really striking now that the efficiency is higher, we can generate this gapped putative zero resistance state, even at room temperature. Okay, if this is done at room temperature, I'll show you the spectra taken at 295 Kelvin. Where, you know, the gap is not great, but sigma 2 diverges and the reflection coefficient is just a little bit below 1. And so this is the last point as far as we could get. We couldn't squeeze the laser anymore, but certainly this gap is getting larger and larger and larger as you know, with fluence, yeah. Anyway, the fit gives you something that is of order 0. About 12 milli, the gap frequency is about 12 millieV, with the caveat that, as you well know, potassium C60 has a large polaron here. So it's not clear whether we're seeing the gap. Because remember, if you look at the George's data, which is that, you know, what you see is that really the gap is not closing. It's being filled in from below. And the gap kind of stays fixed, but it's never clear whether this thing is a gap or a polaronic. Anyway, longer. 12 millieV as opposed to 4. Yeah, larger than the equilibrium gap, let's say. So this is metastable. It's much more efficient, and it happens at very high temperatures, this state. So let me tell you what I'm trying to do now. We have a group of extremely talented people who are trying to measure the light-induced Meissner effect. And so this is led by Michele Buzzi, who's a staff scientist in my department. Gregor Iozzo is a postdoc. He's actually a very interesting person who worked in cold gases before and joined our group to do ultrafast. And Giovanni De Vecchi is a PhD student who's also very good. And the way the experiment is being done is the following. This is the gray thing is supposed to be the potassium C60. This is a coil that generates a magnetic field. So we want to do an in-field excitation experiment. You don't want to, you know, the equivalent of an in-field cooling experiment. What you want to see is not that B dot is 0, because that you know already from the optical properties. You want to know that B is 0 in the constant field. And so what B does is it threads the superconductor. This is a magneto-optical material, like a garnet. And what we're trying to do is to do in this case, a magneto-optical Kerr effect measurement, whereby diagnosing the state of polarization of the reflected light we can measure what the size of the magnetic field is as a function of position on the sample after the pulse has been after the pump pulse has been applied to C60. So if this calculated magnetic field changes in time, we ought to be able to see this. We're also experimenting with other coils to see whether we could measure sort of changes in coupled coils after photoexcitation. This experiment kind of works. Sometimes we get very excited, but then we're not 100% sure whether what we're seeing is right. But this is something that we're working on very hard. And the second thing that is also that we're doing with now with quite conclusive information, we've learned how to grow C60 now in these waveguide devices, where we use photoconductive switches. These are the so-called Austin switches that allow you to measure transport with femtosecond time resolution. And we now probed critical current behavior in the light-induced state. And you could compare this to the equilibrium metal where there is no critical current. And you can see critical currents that are somewhat larger than the ones you get in equilibrium. And there's a whole sort of discussion to be had there. So I should say the last thing. So, what is the mechanism? We don't know. If I had to, the working hypothesis, which we are exploring at the moment, is some sort of parametric process where this time-dependent modulation at 50 millieV, say at relatively high energies compared to the energy scales where you want to manipulate the pair coherence, sort of this type of almost super radiant type scheme allows you to manipulate the coherent state by driving this high frequency excitation. And the reason why we think this is the case is that if you look at the earliest time delays before the system is set into this long-lived reflectivity equal 1 state, we find consistently an amplification of the probe pulse. So there seems to be some coherent parametric process where basically at early times you get more probe light than you put in there. So there's clearly something that is non-thermally being pumped at the beginning, and we don't really, we have various theories about this, but we're trying to substantiate this experimentally. So, how much time do I have?
3 minutes and then we start.
Okay, great. I'm not going to tell you about pair density waves because I had a whole sort of story about pair density waves, but this is, I think, is much better. And so I am going to stop here. Do you want me to show the picture now?